Hello friends, welcome to my lecture on discrete Fourier transforms. There will be two lectures on this topic. We have the first lecture now. So, in the discrete Fourier transforms, the discrete data sets are converted into a discrete frequency distribution. We shall see that the discrete data sets are converted into a discrete frequency distribution. Now, since the resulting frequency distribution is discrete, the computers commonly use discrete Fourier transform calculations when frequency information is required. Now, the DFT is also a numerical variant of Fourier transform. Let us see how the motivation for DFT came about. The complex Fourier series of f with period p is given by sigma n equal to minus infinity to infinity dn e to the power minus in omega naught x, where omega naught is suppose 2 pi over p. The values of these Fourier coefficients dn's are given by 1 over p integral over minus p by 2 to p by 2 f t e to the power minus in omega naught t dt when n is taking values 0, plus minus 1, plus minus 2 and so on. The numbers dn's are called the complex Fourier coefficients of n. Since f is given to be p periodic, we may replace this integral over minus p by 2 to p by 2 by any other integral where the length of the interval is p. Okay. So, we can replace integral over minus p by 2 to p by 2 by integral over 0 to p by 2. So, dn equal to 1 over p integral over 0 to p f t e to the power minus in omega naught t dt, where n is equal to 0, plus minus 1, plus minus 2 and so on. Now, to motivate the definition of DFT, suppose we want to approximate the value of dn. Okay. Suppose we want to, because we have to calculate this integral, we can consider numerical integration. So, if we want to approximate the value of dn, okay, then one way is to subdivide 0 p interval, okay, 0 p interval be subdivided into n subintervals of equal length p by n and choose a point t j in each subinterval j p by n to j plus 1 p by n for j equal to 0, 1, 2 and so on up to n minus 1. This is your interval 0 p divided by divided into n subintervals of length p by n each. Okay. So, suppose your j, this interval is j p by n j plus 1 p by n. Okay. The length of each subinterval is p by n. So, this we do for I mean this is the jth subinterval where j takes values from 0 to n minus 1. Now, approximate this dn by Riemann sum. Okay. So, 1 over p sigma j equal to 0 to n minus 1 f of t j. Okay. T j is any point in this interval. So, f of t j e to the power minus in omega naught is 2 pi over p. Okay. So, we put 2 pi over p for that, and then we have t j. Okay. So, we put here k t j because we want the value of dk. Okay. So, dk is k t j here, instead of n now we are writing k. Okay. So, e to power minus 2 pi I k t j by p, and then we multiply by the length of the subinterval. So, this length is p by n. Okay. Of each subinterval, the length of each subinterval is p by n. Okay. So, now this is what, this p will cancel with this p. Okay. And take t j to be let us say, okay. So, here we will take it later the t j to be j p by n. Let us first simplify this. So, 1 over n, okay, sigma j equal to 0 to n minus 1 f t j e to the power minus 2 pi I k t j by p. Now, choose t j to be equal to j p by n. T j can be any point in this subinterval. So, we choose t j to be j p by n. If you choose t j to be j p by n, then what do we get? We get 1 over n sigma j equal to 0 to n minus 1 f t j e to the power minus 2 pi I k j by n. If t j equal to j p by n, okay, then what we get here? Put t j to be j p by n. So, we will get 1 over n sigma j equal to 0 to n minus 1 f t j is j p by n into e to the power minus 2 pi I k j p by n p, this p will cancel. Okay. So, we will get 1 over n sigma j equal to 0 to n minus 1 f j p by n e to the power minus 2 pi I k j by n. Okay. This is what we get. Okay. Thus, the n point discrete Fourier transform is defined in such a way that except for the n by 1 by n factor, except this 1 by n factor, the approximating sum is exactly the n point discrete Fourier transform of the numbers f t naught, f t 1, f t 2 and so on f n minus 1. Okay. Specifically we can say, given a vector of n input amplitudes, say f naught, f 1, f 2, f n minus 2, f n minus 1. So, here I write f j for f t j. Okay. F t j I am writing as f j. Okay. So, given a vector of n amplitude, these are n amplitudes such that f naught, f 1, f 2, f n minus 2, f n minus 1, the discrete Fourier transform yields a set of n frequency magnitudes. So, sigma j equal to 0 to n minus 1 f t j e to the power minus 2 pi I k j by n will give us a set of n frequency magnitudes, and the magnitudes will be given by these decays. Okay. K will run from 0 to n minus 1. So, we will get corresponding to n amplitudes. Okay. We will get n frequency magnitudes. Okay. So, let us see how we define the discrete Fourier transform. The n, let n be a positive integer and u be equal to u j, j equal to 0 to n minus 1 be a sequence of n complex numbers, then the n point dft of u, okay, is the sequence du given by du k equal to sigma j equal to 0 to n minus 1 u j e to the power minus 2 pi I k j by n, where k takes values 0 plus minus 1 plus minus 2 and so on. Okay. You can see here, here I have this k taking value infinite number of values 0 plus minus 1 plus minus 2 and so on, but you will see that only n out of those infinite number of values, only n are distinct, remaining are repeated, because it turns out that this duk is a n periodic sequence. Okay. So, the k, when you take the value of k from 0 to n minus 1, those frequency magnitudes are distinct, others are just repeating. Okay. Because of periodicity of order, periodicity with period n. So, here you can see, if you compare this definition if you compare with this definition, okay, then except this 1 by n factor, remaining sum is the same. Okay. We write f t j as u j here, okay, and then e to the power exponential function is the same exponential signal e to the power minus 2 pi I k j by n, here also e to the power minus 2 pi I k j by n, j running from 0 to n minus 1, here also j running from 0 to n minus 1. Okay. Now, we can simplify this notation, duk we write as uk. So, uk is the discrete Fourier transform of the sequence of n numbers u naught, u 1, u 2, u n minus 1. The sequence of numbers is u naught, u 1, u n minus 1, and they are complex numbers. Okay. So, this is the sequence. Now, let us show that the n point dft, this n point dft is periodic with period n. So, we need not write k infinite number of values of k, we can simply write k equal to 0, 1, 2, 3 and so on up to n minus 1. Okay. So, let us see how it is periodic with period n. So, this is a sequence, okay, given sequence of n amplitude magnitudes, and we want to show that uk plus n equal to uk for any k. Okay. uk plus n by definition you can see uk plus n is sigma j equal to 0 to n minus 1 uj e to the power minus 2 pi I k plus n into j by n. Okay. E to the power minus 2 pi I j k plus n by n. We can separate it into two parts, e to the power minus 2 pi I j k by n into e to the power minus 2 pi I j n by n. Okay. So, this n will cancel with this. Okay. Now, e to the power minus 2 pi I j, this is equal to e cos 2 pi j minus I sin 2 pi j. Okay. J is an integer, okay. And when j is an integer, cos 2 pi j equal to 1, sin 2 pi j equal to 0. So, this is equal to 1, okay, when j varies from 0 to n minus 1. Okay. So, this becomes this quantity becomes e to the power minus 2 pi I j k y n, okay. This is equal to 1, okay. So, we get this, and this is equal to u k. So, the u k is discrete Fourier transform is n periodic, and therefore, u k is equal to this. We can write u k as sigma j equal to 0 to n minus 1 u j e raised to the power minus 2 pi I j k by n, where k varies from 0 to 1 to and so on up to n minus 1, okay. Because u n will be nothing but u naught, u n plus 1 will be equal to u 1, okay, like this. Okay. So, when you take k equal to n or you take k equal to n plus 1 and so on, this will be simply u naught, u 1, u 2 and so on. So, it will repeat. Similarly, for negative values of k. Now, let us see how the discrete Fourier transform is related to the discrete time Fourier transform. If we take the discrete time Fourier transform of a given sequence x n equal to minus infinity to infinity, we get a continuous frequency distribution, okay. Continuous frequency distribution we get, and it is defined as x e to the power I omega equal to sigma n equal to minus infinity to infinity x n e to the power minus I omega n with inverse DTFT, okay. This is inverse DTFT, discrete time Fourier transform. This is discrete time Fourier transform, this is inverse discrete time Fourier transform. So, inverse discrete time Fourier transform is given by x n equal to 1 over 2 pi minus infinity to infinity x e I omega e to the power I omega and d omega. Here you can see that x e I omega is a continuous frequency distribution, we are considering integral, okay. So, it is a continuous frequency distribution and it is 2 pi periodic, x e to the power I omega, you can see x e to the power I omega plus 2 pi if you consider, okay. Then this is sigma n equal to minus infinity to infinity, okay, x n e to the power minus I omega plus 2 pi into n, okay. So, this is e to the power minus I omega n into e to the power minus 2 n pi I 2 n no 2 pi n I, okay, 2 pi n I. This value is equal to 1. So, we have e to the power minus I omega n. So, this is equal to sigma that is x omega e I omega. So, it is continuous frequency distribution with period 2 pi. Okay. Now, if we sample x e I omega at n equally spaced locations, omega k equal to 2 pi k by n, okay. K varies from 0 to n minus 1, the result will be DFT x k. Now, let us see how we get that. See here you take x e I omega k, okay. So, this is sigma n equal to minus infinity to infinity x n e raised to the power minus omega is 2 pi k by n. So, we have 2 pi I k n by n, okay, 2 pi I k n by n. Now, x n is defined only for this range, okay, 0 to n minus 1, okay. So, this sum will be reducing to when we replace x e to the power, okay, x e to the power I omega k we consider as xk, okay, r xk, okay, xk equal to sigma n equal to minus infinity to infinity xn e raised to the power minus 2 pi I k n by n. Okay. So, we take omega k equal to 2 pi I k by n, okay, and consider this at equally spaced locations, okay, equally spaced locations, and these are n equally spaced locations. Okay. So, then the sequence x n is taken to be defined for n varying from 0 to n minus 1. Okay. So, this will be x k, x k will be sigma n equal to 0 to n minus 1, okay, x n e raised to the power minus 2 pi I k n by n, okay, and which is nothing but DFT, DFT of x n sequence. If x n sequence is given for n equal to 0, 1, 2, 3 and so on up to n minus 1, okay, and the remaining values we can take as zeros, then this x n, then this x e I omega reduces to DFT. Okay. So, let us now consider that there is another method of computing the discrete Fourier transform. This is by matrix method. Let us denote W n e to the power minus 2 pi I by n by W n. We have x k equal to sigma n equal to 0 to n minus 1 x n e raised to the power minus 2 pi I k n by n, okay, 2 pi I k n by n. So, e raised to the power minus 2 pi by n we denote by omega n. So, this is sigma n equal to 0 to n minus 1 x n omega w n k n, okay, x n w n k n. So, this is what we get, okay, x k equal to sigma n equal to 0 to n minus 1 x n w n k n, and equivalently we can write it in the form of a matrix equation x equal to d n x. Okay. So, x is this vector x k, x is column vector x 1, x 2 and so on x naught, because k takes values from 0 to n minus 1. So, we get here x naught, x 1, x n minus 1, this is equal to x. Okay. d n is this matrix, d n is this matrix multiplied by x. This small x is the time domain sequence, time domain sequence is that x n sequence. Okay. So, x naught, x 1, x n minus 1. Okay. So, x is this one, x is this one. Okay. Capital X is the frequency resulting frequency information column vector, this frequency information, and this n by 1 column vector is the time domain sequence. Okay. So, x is this one. Okay. So, we have like this x naught, x 1, x n minus 1 equal to d n matrix into x. Okay. So, this d n is n by n matrix. Okay. This is n rows n by 1 matrix, this is also n by 1 matrix, d n is n by n matrix. Okay. Okay. So, this x k can be written in this form. Okay. Let us see how we are writing it. Okay. We are x k equal to sigma n equal to 0 to n minus 1 x n w n k n w n k n. Okay. Now, let us see how we write it. See, x is this one x naught, x 1, x n minus 1. Okay. And small x is small x vector is that time domain sequence. So, x naught, x 1, x n minus 1. All right. Now, so we let us write d n sequence. Okay. d n Dn matrix. Dn matrix will be okay. So, see k varies on this this Wn Kn, k varies along the rows, okay, and n varies along the columns. So, n varies along the columns and k varies along the rows. So, first we write when k is equal to 0, n equal to 0, k varies from 0 to n minus 1 and n also varies from 0 to n minus 1. Okay. So, when so when this is 0, 1, 2 and so on n minus 1 columns. Okay. Here k equal to 0, then k equal to 1 and then k equal to 2 and then k equal to n minus 1th row. Okay. So, when k is 0, n is 0, Wn 0 0, Wn is equal to, we have taken Wn to be equal to e to the power minus 2 pi I by n. Okay. 2 pi I by n. So, Wn Kn is equal to e to the power minus 2 pi I by n into Kn. Okay. So, when k equal to 0, n equal to 0, we will have Wn 0 0, Wn 0 0 equal to Kn is 0. So, e to the power 0 is 1. So, we get first element 1. Now, in the first row k is 0. Okay. So, k is 0 means Wn Kn equal to 1 when k equal to 0. So, all elements are 1. Okay. Similarly, Wn Kn equal to 1 when n is equal to 0. Okay. That is 0 first column. Okay. So, 1, 1 and so on 1. Okay. Then you have in this first row, okay, k equal to 1 and then n equal to 1. So, we get Wn 1 1. Okay. Wn 1 1 product I am writing. Okay. 1 into 1 is Wn 1. Then you write Wn k equal to 1, n equal to 2. So, you get Wn 2 and so on Wn k into n. K is 1, n is n minus 1. So, we get n minus 1. Here k is equal to 2, okay. K is equal to 2, n is equal to 1. So, we get Wn 2. Then k equal to 2, n equal to 2. So, Wn 4, okay, and so on. We get k equal to 2, n equal to n minus 1. So, Wn 2 times n minus 1. Okay. And then we can similarly write last row. Okay. K is equal to n minus 1, n equal to 1. So, we get Wn n minus 1. Then k equal to n minus 1, n equal to 2. So, Wn n minus 2 and so on. We get Wn lastly k is n minus 1, n is n minus 1. So, n minus 1, n minus 1. Okay. This is how we write the matrix Dn. If this matrix Dn when multiplied by x 0, x 1, x 2, xn minus 1 equated to this column vector will give us the all the n equations here. Okay. There are n equations k equal to 0, 1, 2 and so on up to n minus 1. Okay. So, we write these n equations in the form of a matrix equation like we do in the case of solution of a system of linear equations. Okay. So, here this is the matrix. This when you write this DFT in the matrix form, it is easy to compute as we shall see by examples. Okay. So, let us now move on to examples. Let us consider a 3-point DFT. Okay. 3-point DFT is means n is equal to 3, n equal to 3. Okay. This DFT is called as n point DFT. Okay. So, we are given n equal to 3. Okay. Now, xk therefore, sigma n equal to 0 to n minus 1, n equal to 0 to n minus 1 means n is equal to 0 to 2 xn e to the power minus 2 pi I kn by 3, 3 is n. Okay. K equal to 0, 1, 2. So, then the two-dimensional matrix, okay, this is called as the two-dimensional matrix. This matrix D is called the two-dimensional matrix. Okay. So, two-dimensional matrix Dn is equal to D3 will be, now let us see. Okay. So, 1 1 1, 1 Wn1 Wn2, 1 Wn2 Wn4. Okay. So, this is what you get, n is equal to 3. So, 1 1 1, 1 W31, W32, 1 W32, W34. As I said here, k varies along the rows, okay, and n varies along the columns, okay, and this is the matrix Wn Kn, okay, Wn Kn. K varies along the columns from 0 to n minus 1, and n varies along the, k varies along the rows, n varies along the columns. Okay, now let us note one thing, Wn is equal to e to the power minus 2 pi I divided by n. Okay. So, okay, n is equal to 3. So, W33 will be e to the power minus 2 pi I by 3 raised to the power 3, okay, W33. Okay, Wn Kn means Wn raised to the power Kn. Okay, so, W3 to the power 3 will be e to the power minus 2 pi I. So, we get equal to 1. Okay, W3 raised to the power 4. Okay, W3 raised to the power 4 when we have, we can write it as W3 raised to the power 3 into W3 raised to the power 1. So, W3 raised to the power 3 is 1. So, we can write it as W31. Okay. So, when we have n point DFT, in n for n point DFT, we have to note that Wnn is equal to 1. Okay, Wnn equal to 1. So, any power of Wn more than n, okay, can be reduced to a power less than n. Okay, Wn, say Wn raised to the power n plus 2. Okay, if you have, you can write it as Wn to the power 2. Okay. So, here we have W31, W32, W32, W34. W34 will be equal to W33 into W31. Okay, and W33 is 1. So, we get W31. Okay. So, this will be, this matrix will be 1 1 1, 1 W31, W32, W32, and then W31. Okay. If we have a n point DFT, the power of Wn, if it is n, it will be 1. If it is more than n, it will be can be reduced to power less than 1, less than n. Okay. Now, let us see what is W31. W31 equal to W3 is e to the power minus 2 pi I by 3. So, it is cos 2 pi by 3 minus I sin 2 pi by 3, and its value is cos 2 pi by 3 is minus half, sin 2 pi by 3 is root 3 by 2. So, minus I root 3 by 2. Okay. So, this is W31, and W32, W32 is e to the power minus 2 pi I by 3 raised to the power 2. So, e to the power minus 4 pi I by 3. So, this is cos 4 pi by 3 minus I sin 4 pi by 3. Cos pi by 3 is cos 4 pi by 3 is cos pi plus pi by 3. So, that is minus cos pi by 3, and minus cos pi by 3 is minus half. Okay. Sin 4 pi by 3 is sin pi plus pi by 3, which is minus sin pi by 3. So, minus root 3 by 2. So, this is plus I root 3 by 2. Okay. So, you get this value. So, W31 is this, W32 is this, W32 is same, this is minus half plus I root 3 by 2, we have calculated already, and this W34 we have seen, W34 is W31. W31 we have already found, this is minus half minus I root 3 by 2. So, this is how we calculate D3. Now, let us consider a 4-point DFT. When you consider a 4-point DFT, that is n equal to 4, xk will be sigma n equal to 0 to 3 xn wn kn. Okay. Tweedle matrix will be what? Again let us see, let me write Tweedle matrix for n equal to 4. Okay. So, Tweedle matrix. Okay. So, this is equal to W n k n, okay, where k runs from 0 to n minus 1 and n runs from 0 to n minus 1. As I said, Tweedle matrix d n be denoted by d n, and d n is given by, okay. So, k varies along the rows. Okay. This is k equal to 0, k equal to 1, k equal to 2, k equal to 3 and so on, k equal to n minus 1th row. And here n equal to 0th column, n equal to 1 first, n equal to 1 column, 2, n equal to n minus 1. So, n equal to 0 is the first column, n equal to 1 is the second column. Okay. W n k into n, when k is 0 or n is 0, okay, W n to the power 0 means 1. Okay. So, this is 1, this is 1, this is 1, 1. Okay. Either k is 0 or n is 0, and then when n is 0 in the first column we also have 1. Then first k equal to 1, n equal to 1. So, we get W n to the power 1. When k is 1, n is 2, we get W n to the power 2. Okay. When k is 1, W n n equal to n minus 1, we get W n to the power n minus 1, okay, because k is 1. Then k is 2, so we get W n 2 into n is 1, okay. Then W n 2 into 2, that is 4, and then W n 2 into n minus 1, and so on. Lastly, we write k n minus 1. So, W n, okay, k is n minus 1, n is 1. So, we get n minus 1. K is n minus 1, this is n is 2. So, 2 times n minus 1, and we get W n minus 1, oh sorry, W n minus 1 into n minus 1. Now, let us put n equal to 4 in this general matrix. So, 1 1 1 1, okay, 1 1 1, okay. Then we get W 4 1, okay, W 4 2, and we get n equal to 4, W 4 3, okay, n equal to 4. Then we get W n 2, okay, W n 4, then we get n equal to 4. So, okay, so this is W n 6, okay. Then 1 W n to the power 3, W n to the power 4 minus 1. So, that is 4 into 2, no, 4 minus 1 is 3, 3 into 2 is 6, and then 4 minus 1 is 3, 3 into 3 9. So, W n 9. Okay. Now, we can reduce it using the fact that W n to the power n is equal to 1. Okay. So, this can be written as further 1 1 1 1 1 W 4 1, W 4 2, W 4 3, then 1 W 4, this n should be 4 here, okay, everywhere. Okay, W 4 2, W 4 2, W 4 4 is 1, okay, W 4 4 is 1, W 4 6 is W 4 2, then 1 W 4 3, then W 4 6 is W 4 2, okay, and this W 4 9, W 4 9 is W 4 4 into W 4 4 into W 4 1. So, W 4 1, okay, W 4 9 equal to W 4 4 into W 4 4 into W 4 1. Okay. Now, W 4 1 is how much? W 4 1 is e to the power minus 2 pi I by 4, okay, raised to the power 1, because W n is e to power minus 2 pi I by n. Okay. So, this is e to the power minus pi I by 2. So, this is cos pi by 2 minus I sin pi by 2. So, this is minus I. Okay. Then W 4 2. Okay. W 4 2 we want. Okay. W 4 2 is W 4 1 square. Okay. So, minus I square. So, this is I square is minus 1. So, we get minus 1. W 4 cube. W 4 cube is minus I whole cube. Okay. So, minus I whole cube means minus 1 whole cube is minus, okay. I cube is I square into I square is minus 1 into I. So, plus I. Okay. So, we got the value of W 4 1, W 4 2, W 4 3. Okay. So, let us put these values. So, then what do we get? The matrix as 1 1 1 1 1 1 1, W 4 1, W 4 1 is minus I, W 4 2, W 4 2 is minus 1, W 4 3 is I, okay, and then W 4 2, W 4 2 is minus 1, W 4 1, W 4 4 is 1, okay, W 4 2, W 4 2 is minus 1. Okay, and then W 4 3, W 4 3 is I, okay, W 4 2, W 4 2 is minus 1, and W 4 1, W 4 1 is minus I. So, let us see whether we have the same matrix here. Okay, so, we have this matrix, okay, D 4 is this matrix, W 4 0, W 4 0 is nothing but W 4 4, okay. So, this is equal to 1. All right. So, let us see whether we have the same values or not. We have x 0, x 1, x 2, x 3. This is the left hand side frequency domain column. This is the amplitude column. This one. This is the amplitude. We are taking an example here. Here you can put the values. Okay. Let me see. I have not put the values here. This is equal to if you put these values which I have calculated. This is equal to 1 1 1 1, and then you get 1, and W 4 1 is equal to minus I, and W 4 2 equal to minus 1, W 4 3 equal to I, okay, and then we have 1, W 4 2 equal to minus 1, W 4 0 equal to 1, W 4 2, W 4 2 equal to minus 1, okay. And then we have 1, W 4 3 is I, W 4 2 is minus 1, and W 4 1 is minus I. So, let us see first row, first column, they are always 1. In the second row we have 1 minus I minus 1 I, okay, 1 minus I minus 1 I, 1 minus I minus 1 I. So, okay, then we have here 1 minus 1, 1 minus 1. So, we have 1 minus 1, 1 minus 1, and then we have 1 I minus 1 minus I, 1 I minus 1 minus I. Okay. So, this is how we calculate this D 4. Now, let us take an amplitude matrix and let us determine the corresponding frequency matrix. Okay. So, this is time domain. Okay, time is vector 1 minus 1 I minus I. Okay. So, 1 minus 1 I minus I, and these are the values of this is the D 4 matrix. Let us check. So, we multiply by 1 minus 1 I minus I to this matrix, and what you get in the numerator, in what you get here, this matrix has 1 plus 1 minus 1 I minus I. Okay, when you multiply this column to first row, when you multiply this column to second row, what you get 1 and minus I into minus 1. So, we get plus I, and minus 1 into I is minus I, 1 minus I into I is minus I square. So, plus 1. Okay. And then when you can multiply to this, here 1 minus 1 is plus 1, and then here I we have, and here we get plus I. Okay. So, then we can get similarly last column last row we multiply by this, and we get 1 1, then we get minus I, we get minus I, we get plus I square. So, minus 1. Okay. So, this cancels with this cancels with this, and this cancels with this, and here we have 1 cancels with 1. So, this is what you have 0, and then you have 2, you have 2 plus 2 I, and we have minus 2 I. Okay. So, this is what we get. So, x naught equal to 0, okay, x 1 equal to 2, x 2 equal to 2 plus 2 I, and then x 3 equal to minus 2 I. So, we can get the frequency magnitudes when you know the time amplitudes. Okay. So, let us consider the constant sequence. Suppose we are given the constant sequence u j, here u equal to c, j equal to 0 to n minus 1. We have taken u equal to u j, okay, j equal to 0 to n minus 1 as the sequence. So, here we are given u j as c for all j. Okay. So, if you want here u k equal to sigma j equal to 0 to n minus 1, u j is c e to the power minus 2 pi I j k by n. Okay. C can be taken outside because it is constant, and then this is a geometric series. Okay. This is a geometric series, you can see, and the ratio is e to the power minus 2 pi I k by n. Okay. Geometric ratio R is e to the power minus 2 pi I k by n. So, we can sum it up. Sum will be 1 minus e raised to the power minus 2 pi I k by n raised to the power, because there are n terms. So, raised to the power n divided by 1 minus e raised to the power minus 2 pi I k by n. Okay. Now, here what will happen? This is c times 1 minus e raised to the power minus 2 pi I k by n into n. So, we get e to the power minus 2 pi I k divided by 1 minus e raised to the power minus 2 pi I k by n, and k is an integer. Okay. So, e to the power minus 2 pi I k will be equal to 1. Okay. So, this is 0, okay, as e raised to the power minus 2 pi I k equal to 1. Okay. So, if we take a constant sequence, then its discrete Fourier transform is 0 for all values of k. Okay. K is we are writing 0 plus minus 1 plus minus 2 and so on, as we have already seen. U k is a n periodic sequence. So, we can reduce this k to 0, 1, 2, 3 and so on up to n minus 1. Okay. Now, let us say we take another example. Suppose x n is a to the power n, where a is a complex number, then the discrete Fourier transform of the sequence x n k is given by sigma k n equal to 0 to n minus 1 a to the power n e to the power minus 2 pi I n k by n, and this can be written as sigma n equal to 0 to n minus 1 a e raised to the power minus 2 pi I k by n whole to the power n. Okay. So, this is a geometric series again. Okay. So, sum will be 1 minus a e raised to the power minus 2 pi I k by n whole to the power n, okay, divided by 1 minus a e raised to the power minus 2 pi I k by n. Okay. Now, this will be equal to, if a is equal to 2 pi I k by n. Okay. If a is equal to 2 pi I k by n, yeah, okay, here you can see, that if a is equal to e raised to the power 2 pi I k by n. Okay. We can divide by this only when a is not equal to e to power 2 pi I k by n. If a is equal to e to power 2 pi I k by n, then this will be equal to 1, okay, and we will have sigma n equal to 0 to n minus 1, okay, 1, okay, which is equal to n. So, if a is equal to e to the power 2 pi I k by n, then we get the dx n k equal to n for all k values of k, okay. And if a is not equal to d to e to the power 2 pi I k by n, then we get this. So, here when you raise it to power n, we get 1 minus a to the power n, because e to the power minus 2 pi I k will be equal to 1. So, we get the, if a is not equal to e raised to the power 2 pi I k by n, this is, here we are taking a not equal to e raised to the power 2 pi I k by n, okay. So, then we get 1 minus a to the power n divided by 1 minus a e raised to the power minus 2 pi I k by n. And if a, as I said, if a equal to e to the power 2 pi I k by n, we get the value 1 d x n k. Is equal to n for all k, okay. So, this is how we do this problem. If x n is the binomial coefficient n minus 1 c n, okay, then x k is again d of x n at k, okay. So, that we are writing as x k, sigma n equal to 0 to n minus 1 x n e to the power minus 2 pi I k n by n. So, this is sigma n equal to 0 to n minus 1 c n e to the power minus 2 pi I k n by n, and this can be regarded as sigma k equal to 0 to n minus 1 c n e to the power minus 2 pi I k by n raised to the power n, okay. So, then this by binomial theorem, this is nothing but 1 plus, if it is suppose alpha, then 1 plus alpha to the power n minus 1, okay. Alpha is e to the power minus 2 pi I k by n, okay. So, this is 1 plus e raised to the power minus 2 pi I, and this I am writing as alpha, okay. Okay. So, this how we can do this problem again for k equal to 0, 1, 2, 3 and so on up to n minus 1. Now, if this is a very important question, if x n is a real sequence, okay, we are going to show that if x n is a real sequence, then the discrete transform sequence of x n is also real, okay. So, let x n belong to R, then d x n k equal to x k equal to sigma n equal to 0 to n minus 1 x n e raised to the power minus 2 pi I k n by n, by definition we have this, okay. Hence, let us take the conjugate of x k. We want to show that x k is real for every k. So, let us take conjugate of this, and we shall then show that x k bar is equal to x k for every k. So, x k bar equal to sigma n equal to 0 to n minus 1 x n bar, and the conjugate of e to the power minus 2 pi I k n by n is e to the power 2 pi I k n by n, okay. Now, x n is real, so x n bar equal to x n, okay. So, this is because as x n is real. So, x n bar equal to x n, okay. So, this equation, this is equal to this, okay. Now, let us replace, let us consider x n, this is valid for any k, okay. So, let us consider x bar n k, there k can be, here k varies from 0 to n minus 1, okay. K varies from 0 to n minus 1, okay. So, let us replace k by n minus k then, okay. So, x bar n minus k will be from here sigma n equal to 0 to n minus 1 x n e to the power 2 pi I, we are replacing k by n minus k. So, n minus k into n by n, and we can write it into two parts, e to the power 2 pi I n into n by n, and the other part is e to the power minus 2 pi I k into n by n, okay. So, this n cancels with this, e to the power 2 pi I n is equal to 1, e to the power 2 pi I n is equal to cos 2 n pi plus I sin 2 n pi. So, this is equal to 1 because n is an integer. Okay. So, we get this is equal to 1, we get only this. Okay. So, we get x n e to the power minus 2 pi I k n by n, which is equal to x k. So, x bar n minus k is equal to x k. Now, let us put k equal to 0 in this. Okay. Let us put k equal to 0. So, what do we get? X n var equal to x 0. Okay. X n var equal to x 0. Now, we know that x 0, x 1, x 2, x n minus 1 is an n periodic sequence. Okay. So, x n is equal to x naught. Okay. X n equal to x naught. So, what do we get? X naught is equal to x n var. Okay. X naught equal to x n var. So, and x n is equal to x naught. So, x n bar is equal to x var now, x naught var. Okay. We know that x naught, we have found that x naught equal to x n bar, but because of n periodicity x n is equal to x naught. So, combining this and this, okay, we get x naught equal to x n bar equal to x naught var. So, x naught is equal to x naught var. So, this means that x naught is real. Okay. Similarly, we can take k equal to 1, 2, 3 and so on up to n minus 1 and show that x k is equal to x k var for all k. Okay. So, we can show for other values of k that x k is real. Okay. So, x k is real. If the input sequence is real, the output is also real. So, we get real DFT. Okay. Now, linearity property, if u equal to uj, j equal to 0 to n minus 1, b equal to bj, j equal to 0 to n minus 1 are sequences of complex numbers and ab are complex constants, then d of au plus bbk equal to d a duk b dvk. Okay. So, this we can easily show d of au plus bk by definition is equal to sigma j equal to 0 to n minus 1 a u j plus b b j e raised to the power minus 2 pi I j k divided by n. Okay. Now, since this is a finite summation, I can write it as a u j plus b b j, b break into two parts, then take a and b common. So, a times a and b out. So, a times u j plus b times okay. So, this is a times T u k plus b times d v k. Okay. So, this discrete Fourier transform satisfies linearity condition, it satisfies linearity property. Okay. Now, let us consider this problem u equal to sin j, j equal to 0 to n minus 1, where a is any complex number and it is not an integer multiple of pi. Okay. So, then if you find the discrete Fourier transform of this sequence, then u k by definition will be equal to sigma j equal to 0 to n minus 1 sin j e to the power minus 2 pi I j k by n. Okay. And let us put then the value of sin j. Sin theta we know, sin theta equal to e to the power I theta minus e to the power minus I theta by 2. Okay. So, sin j we can put similarly. So, u k equal to sigma j equal to 0 to n minus 1 e raised to the power I j a minus e raised to the power minus I j a divided by 2 I multiplied to e to the power minus 2 pi I j k by n. Okay. So, now let us use linearity property. So, by linearity property we have 1 over 2 I times sigma j equal to 0 to n minus 1 e to the power I j a e to the power minus 2 pi I j k by n, and then sigma j equal to 0 to n minus 1 e raised to the power minus I j a e to the power minus 2 pi I j k by n. Okay. Now, we can write let us find some of this. So, this is actually can be written as 1 over 2 I sigma j equal to 0 to n minus 1 e to the power I a sin e to power I a e to the power minus 2 pi I k by n raised to the power j. Okay. And then similarly the other one sigma j equal to 0 to n minus 1 e to the power minus I a e to the power minus 2 pi I k by n raised to the power j. Okay. They are both geometric series. Okay. So, we can write it sum. So, we have 1 over 2 I sigma j equal to 0 to n minus 1 e to the power I a minus 2 pi I k by n. Okay. 2 pi I k by n raised to the power j. Okay. So, then we have this, and then we have sigma minus we have in the middle sigma j equal to 0 to n minus 1 e to the power minus I a minus 2 pi I k divided by n raised to the power j. Okay. And we can write it sum 1 over 2 I. So, this is geometric series. So, 1 minus e to the power I a minus 2 pi I k by n raised to the power n. Okay. Divided by 1 minus e to the power I a minus 2 pi I k divided by n. Okay. Here we will have 1 minus e raised to the power minus I a minus 2 pi I k divided by n whole to the power n divided by 1 minus e to the power minus I a minus 2 pi I k divided by n. Okay. Now, this is nothing but 1 over 2 I 1 minus e to the power I a n 1 over 1 minus e to the power I a minus 2 pi I k by n. Okay. And then minus 1 minus e raised to the power minus I a n divided by 1 minus e raised to the power minus I a minus 2 pi I k by n. This is because e to the power minus 2 pi I k by n raised to the power n is equal to 1. Okay. So, this is what we get, okay, as the answer to this problem. Okay. Now, so with this I would like to end my lecture. Thank you very much for your attention.